Very good afternoon, friends, and in this video we are going to discuss about this very popular theorem called as differentiability and continuity. You have to find whether the differentiable function is continuous or the continuous function is differentiable. The statement goes like this: if a function fx is differentiable at a point, it is necessarily continuous at that point, but the converse is not true. It means every differentiable function is continuous at the point, and every continuous function may not be differentiable. This always goes like this. So how to prove this statement? Now suppose if I say that if I have function, suppose you take the point as usual, just like the previous definitions, I take the value at x equal to c, then we find limit x tends to c fx minus fc over x minus c, and this should be a finite quantity, or this limit should exist finitely, so it should have a finite value. And for continuity it goes like limit x tends to c fx, means the limit of the function at the point x equal to c should be equal to the value of the function itself at that very same point. If these two conditions true, then this is called continuous, and if this is true, then this is called differentiation. So we write this as f dash c. Okay, so now here if I want to prove that this function which is differentiable, I better write f dash x at c. It's making more sense. So this is, if I write that f dash x equal to limit x, if this is true, because this says that function is differentiable, so this statement is true. So this one is a finite quantity, and we have to prove this like the limit x tends to c. So we can design a new function like fx can be written as fx minus fc upon x minus c into x minus c plus fc. Now check it out nicely. Fx minus fc over x minus c into x minus c. The denominator cancel. You have just only fx minus fc, and when you add fx to this, it will become only fx. So fx equal to fx. Now if I apply limit x tends to c in both cases, like here limit x tends to c fx minus fc over x minus c, since there are three functions and here this and this is in product form, so we will simply write like this, and we'll write the limit for this also. Limit x tends to c, and this is x minus c plus limit x tends to c fc. So fc looks like a constant function because you have already put the value of c in the function, so it will give you just numerical value. That is a constant function. Now this part is nothing but, by definition, it is f dash x into, if you put the value of x as c in this normal, because this is defined everywhere, so if you write x minus c, so c minus c will become 0, so this is c minus c, and then plus last one, it will remain fc, because x tends to c and this is not a function of x, this is a constant function, so it will remain fc irrespective of wherever x goes. So f minus x into c minus c, this part is 0, so this is cancelled, and you have only 0 plus fc, that is fc. So we have been able to prove limit x tends to c fx equal to this, and this one is what desired to prove that the function is continuous. Means by proving this, I proved that a differentiable function, because I have used this function precisely here. So using this proper information, because I assume that my function was differentiable at the point x is c, and then I was able to prove that the limit x tends to c fx is fc, means this function is continuous. Otherwise, so we can say that this statement is properly true. And what the statement says again, Before this, I would like to explain a function f(x) is differentiable at each and every point in its domain, or here at take any point. A function f(x) is differentiable at a point. It is necessarily continuous at that point, but converse is not true. Means a function which is differentiable can always be continuous at that point, but if a function is continuous, it may not be differentiable at the very same point. This theorem is all about this rule. So now I would like to take some examples to prove the statement, and then for that I need just to clear up this mess. Suppose I have a function f(x) equal to mod x, and I want to check its limit, means its continuity and the differentiability at x equal to 0. So first I go for continuity. So continuity test, whether it's continuous or not, continuity test, and then it goes like limit x tends to 0 minus fx is limit x tends to, now I would like to change this as h tends to 0 as usual, and then I'll replace x as 0 minus h because this is 0 minus. So here I write f(0 minus h). So this becomes limit h tends to 0, and then there I'll get f of minus h, means mod of minus h, and we know that the mod of minus h is, so limit h tends to 0 f of minus h, and my function is this, so this will become limit h tends to 0 mod of minus h, and you know that the mod of minus h equal to h, so this value is simply h, so limit h tends to 0 h, this goes to 0, so the left hand limit value is 0. Now if I go for the right hand limit, so limit x tends to 0 plus fx, here I write LHL, and this is right hand limit so that you can understand it. So this is limit h tends to 0 f(0 plus h) is limit h tends to 0 fh is limit h tends to 0 mod h is limit h tends to 0 h, which is 0. So both the values of the left hand limit and right hand limit are 0, so the limit said to exist, and the value of mod 0 at is also 0. So the value of the limit is 0 and the value of the function is also 0, so this function is continuous. Now check the differentiability test. It goes like R differentiability test. Differentiability test. So LHD, this is limit x tends to 0 minus fx minus f(0) because my c is 0 upon x minus 0. So here if I change the limit as limit h tends to 0, then this becomes limit h tends to 0, and here I write f(0) minus h minus f(0) over, at the place of x here you write 0 minus h, so this is 0 minus h minus 0. Do you see it nicely? Okay, so this value, since okay, I'll for the next part I'll go here. So from here if I come here and then I say this is f of minus h, so f of minus h is mod of minus h, so you will get limit h tends to 0 f of minus h, that is the mod of minus h, and mod of minus h is h, so this is h. This part is f(0) is mod 0 is 0, so I'm not writing that, and below you see this is minus h, so this is minus h, it means this gives you value minus 1. So the left hand derivative's value is minus 1. Now what about the right hand derivative's value? That is RHD. So limit x tends to 0 plus fx minus f0 over x minus 0. Again we'll try to make it as limit h tends to 0, and then there are right 0 plus h to become f0 plus h minus f0 over 0 plus h minus 0. Now from here I come back to this point. So limit h tends to 0, f of h, that is the mod h is h over h, and the f0 is 0. So this is giving me a value of 1. So the left hand derivative gives me a value of minus 1. Right hand derivability test giving me the value of 1. So the left hand limit or left hand derivatives value is minus 1, and the right hand's derivative value is 1. It means these are not equal. So the function is not differentiable at x equal to 0, but it was continuous at x equal to 0. So it means this function is continuous function, and this function is not, if the every, like the theorem states, that I say that if a function is derivable or differentiable at a point, then it is necessarily continuous, but the converse is not true. And this is what we are trying to prove, that the converse is not true, because this function is continuous at x equal to 0 but not at all derivable at x equal to 0. So here I prove this statement and theorem. Thank you very much, and watch our next videos to go deep into the differentiation.